So, Chapter 5, Section 1, okay, deals with trig identities. And some of these are ones that we should already be familiar with. Some of them are going to be new. Okay, but the end result is by the end of this chapter, we will have established around 1 to 2 dozen trig identities, relationships between our 6 trig functions that are true for every angle. That's why they're called identities. Okay? We start with this list of reciprocal and quotient functions, which we should already be aware of. Okay, we already know that sine and cosecant are reciprocals of each other, which means sine is 1 over cosecant, cosecant's 1 over sine. Same with cosine and secant, same with tangent and cotangent. We've been using that fact for well over a chapter now. Okay? These last two over here, these 6 are the reciprocal. Okay, reciprocal is these 6. These are the reciprocal functions. And then these two over here are called the quotient trig identities. Tangent is always the sine divided by the cosine. And cotangent is always the cosine divided by the sine. Those are true for every angle, period. Okay, these are trig identities. They are statements that are true no matter what angle you plug in for theta. They are true for every single angle. And over the next couple sections, we're going to be looking at other groups of identities that will allow us to solve problems, to simplify complex things down into simple things. Okay, that's what we're going to be doing. We're going to be simplifying and solving using these identities. So there's our first 2 sets. The entire reciprocal set we should already be aware of. In theory, we should already be familiar with the blue one there as well, the quotient identities, but those might be new. Okay, so right now, there's 8 trig identities right off the bat. Okay, no matter what angle you plug in, these statements are definitely true 100% of the time. So, next up would be a new set in theory known as the Pythagorean identities. And we're actually going to develop one of those right away here. Okay, think about the first quadrant of the unit circle. So just quadrant 1, positive x, positive y. Remember that on the unit circle, we have a radius of 1 unit, right there. And that each point on the unit circle has coordinates cosine angle, sine angle, no matter what angle that is. No matter whether it's in degrees or radians, that point is cosine comma sine. Which means that we can form a right triangle by dropping down that vertical line. And that x, that distance from the origin to that vertical line, is the cosine of our angle. And y, that vertical distance from the x-axis to the point, is sine of the angle. Okay? We can use our Pythagorean theorem to find a connection between sine and cosine, right there. Okay? But before we do that, we need to talk notationally. Okay? We don't write sine of theta squared. Okay? That's not proper notation. What happens is we write it as sine squared of theta. So anytime you see sine squared, cosine squared, tangent cubed, that means the entire expression is being squared or cubed. Okay? So these are mathematically exactly the same. Sine theta squared is sine squared. That's how we write that. So, Pythagorean theorem on that right triangle in that picture. Okay, which one of those 3 numbers, sine, cosine, or 1, is the hypotenuse? 1. So your C value for Pythagorean theorem would be 1. And your A and your B, those are interchangeable. They stand for the legs, right? So when we set up Pythagorean theorem, and we say a squared plus b squared equals c squared, we get that cosine squared theta plus sine squared theta equals 1. Because 1 squared is still 1. What that means is you can plug in any angle you want for theta, and they'll always equal 1 when you square the cosine and square the sine. Every single time. Okay, that is our first Pythagorean identity. Cosine squared plus sine squared of any angle is always equal to 1. Now, if we take that identity and we divide it by stuff, we can come up with two other identities that are related to the Pythagorean theorem. If we divide this expression by cosine squared, so everything by cosine squared, we get 1 plus tangent squared equals secant squared, which is our second Pythagorean identity. And if we take our Pythagorean theorem base here and we divide everything by sine squared, we get cotangent squared plus 1 equals cosecant squared. So those are our three Pythagorean identities. Now, the one you're going to use way more often than the others is the one we developed using the unit circle. Sine squared plus cosine squared equals 1. That's the one we're going to use the most often. Okay? But those other two identities, those are true for every angle as well. So now we're looking at, we had our 6 reciprocal identities, our 2 quotient identities, and now 3 Pythagorean identities. See how they're stacking up quickly here? Okay, so we want to keep our notes handy so that we do, because we shouldn't need to memorize these. We should be able to look them up. Okay, but we need to keep our identities handy so that we have them. So there's our 3 Pythagorean identities. So, first thing we've got to be able to do is simplify. So here's a couple examples of, we're going to take these expressions, we're going to rewrite them only in terms of sine and cosine, using those reciprocal and quotient identities, and we're going to simplify them down as much as we possibly can. So in example 1, we have cotangent squared times secant plus secant. So in terms of sine and cosine, okay, we need to ask ourselves, what is cotangent in terms of sine and cosine? So look back at that first list. Okay, cotangent is a quotient identity, cosine over sine. Yes, it's in the box. And secant, in terms of sine and cosine only, is 1 over cosine. So what happens is we substitute cosine over sine for cotangent. We substitute 1 over cosine for secant. So we have, okay, we've got cotangent squared, so that's cosine squared over sine squared. That's your cotangent squared. Would you agree with me on that? Times 1 over cosine, because that's secant. Yes? Plus 1 over cosine. Because it says right here we're going to use only sine and cosine, so we're going to rewrite everything in terms of sine and cosine, and then we're going to simplify. So we replace our cotangent with cosine over sine, and it's squared, so they both get squared. Secant with 1 over cosine, because we want to rewrite everything in terms of sine and cosine. That's one of them, but we want to write it in terms of sine and cosine. Look further to the right. Cotangent is also cosine over sine. So now we need to use algebra to simplify this. Does anybody see anything that can cancel? What? Okay, this cosine would cancel in here and cancel out the squared, leaving us with just cosine over sine squared. See it? So that gives us cosine over sine squared plus 1 over cosine. Now, in order to add those expressions together, we would need a common denominator, which would be cosine times sine squared. So to get that, what we do is we multiply the first expression, bottom and top, by cosine. And the second expression, we multiply the bottom and the top by sine squared. Which gives us cosine squared over cosine sine squared plus sine squared over cosine sine squared which does have a common denominator. So when we add those fractions together, when you add fractions, you really are only adding the numerators. So that would be cosine squared plus sine squared over cosine sine squared and according to our Pythagorean identities, cosine squared plus sine squared is 1. So we can replace the numerator. That is 1. So that is 1 over cosine times sine squared. We can't get it any nicer. That's as good as it's going to get. In theory, we could rewrite it as something like secant over sine squared, but that's not really any neater. Okay, that is as simple as that expression can get. Well, we've taken an expression that was 2 terms, and we've combined it down to 1 term, which is mathematically simpler. Long term, we will be using this to solve equations. Okay, short term, we're just trying to get comfortable with working with these identities. So, example 2. Okay, again, we want to rewrite everything that is not sine and cosine in terms of sine and cosine. So in that expression, the only thing we've got that is not in terms of sine and cosine is a single secant squared. So in terms of sine and cosine, secant is 1 over cosine. So we start off by rewriting that expression. We've got cosine of x minus, we're going to replace secant with 1 over cosine, which in this case it would be squared because secant is squared. And then we've still got one other cosine x being multiplied there. So, that's your angle. Yep, that's your angle. Right. No, that's not a multiplication symbol. That's our angle. Our x is the angle value, like theta. It's just our variable representing the angle. So what happens when I multiply 1 over cosine squared times cosine? Yeah, this cosine cancels with the exponent, taking it down to just 1 over cosine. So we end up with cosine x minus 1 over cosine x. Because we can. One's on top, one's on the bottom. If we have the same thing on the top and bottom of any expression, it can be canceled. Just reducing, just like we're reducing a fraction. We basically ended up with cosine divided by cosine squared. That's cosine from the top and bottom can cancel. So now we have two terms. If we get a common denominator, we could combine them into one term. So our next step then would be to get a common denominator. So cosine right now is over 1. And the common denominator would be cosine. So we only need to multiply the first expression, and we need to multiply the bottom and the top by cosine of x to get a common denominator. So that would be cosine squared over cosine minus 1 over cosine. And you may be thinking, but didn't we just cancel something that looked like that? Yeah, we did. But sometimes in order to get to a common denominator, we have to make things more complicated before they get simpler. Now with that common denominator, we combine the numerators, which would be cosine squared minus 1 over cosine. So we're down to one term. No, we cannot cancel it because order of operations says that the subtraction on top here basically has a hidden set of parentheses, meaning we cannot cancel that cosine until we've carried out the subtraction. Now, we can simplify this further, but it's a little tricky. Okay, think back to, we've got that trig, the Pythagorean identity that says cosine squared plus sine squared is equal to 1. Yes? Well, with a little bit of rearranging, if we move the 1 to the left and the sine squared to the right, we can rewrite this equation as cosine squared x minus 1 equals negative sine squared x. Let's use some algebra. We move this term to the right, makes it negative. This is our Pythagorean identity. And the 1 to the left, that makes it negative. So if we switch the sides on the sine squared and the 1, they both become negative, and we get cosine squared minus 1, which is what we have right here on the top of the fraction. Right? So this two-term expression here, which is right there, can be replaced with negative sine squared. And we're not going to get any simpler than that. That's as good as we can do. That's the thing that makes this tricky. I know when I'm done because I've mastered it. You guys are going to have to play with it a little bit. Okay, it's one of those things where the more practice you do, the better you're going to be at it. Okay? The more practice you do, the better you're going to be at this thing. Okay, so Okay, so what does it mean when we say simplify? Because that's what the directions are going to say. They're not going to tell you how to simplify. They're going to say simplify. Simplify means that we have minimized the number of trig expressions, okay, as far as we possibly can. In an ideal world, we would always get to only one, but, well, we won't always make it there, okay? And then a second rule of thumb is we can clean it up a little bit more if we get rid of anything that happens to be in the denominator. And we did not do that on those first two expressions, but we could have cleaned them up a little bit more if we had gone back out of just sine and cosine. By replacing whatever the denominator is with its reciprocal, we could have gotten it down to no fractions, which would have been cleaner in theory. Okay, but those directions read use sine and cosine, so that's what we did. We cleaned it up as much as we could with sine and cosine. Okay, so let's do another one here. This time we will actually get rid of the denominator as well. So notice it doesn't say using sine and cosine, it just says simplify. Okay? So those rules are pretty much the same thing every time. Okay, we're going to change everything to sine and cosine. That is going to be our first step every time. Yes. Everything into terms of sine and cosine will be the first step every single time. So when we look at cosecant, secant minus cotangent. Cosecant is what? 1 over sine. Secant is 1 over cosine. And then we need to break out a quotient identity for cotangent. It is sine over cosine. So we change everything into sine and cosine. You're right, it's cosine over sine. I wrote that backwards. That's tangent, not cotangent. Cotangent's cosine over sine. Apologies. Okay. Now we're going to use our algebra skills and our knowledge of fractions, both of which we know are so very strong, to manipulate this as much as we possibly can. So first off, we have two fractions here that need to be multiplied. When we multiply fractions, what do? Multiply the top, and we multiply the bottom. Yes? So just go straight across. That would be 1 times 1 is 1. Sine times cosine, well, we just write those next to each other. Okay, so we combine those two sets of parentheses into one fraction, 1 over sine cosine. And then that still has minus cosine over sine because that was our cotangent. Okay, now we are going to do common denominator so that we can add those two expressions into one. So a common denominator for these two fractions, we've got a sine in both, but we only have a cosine in the first one, right? So we need a cosine in the second fraction. So we get one by multiplying the bottom of the fraction by cosine, and in order to stay balanced, whatever we do to the bottom, we also have to do to the top. Which turns this into 1 over sine cosine minus cosine squared over sine cosine. So we're going to then combine those two fractions, which is 1 minus cosine squared over sine cosine. And I know I'm not saying theta every time, but the theta needs to be there every time because we're writing out notation here. Theta is the angle we're referring to. It's our variable. Okay? We need to keep the theta in there. If the theta bothers you, feel free to replace it with an x. That's no problem at all. It's just a variable. They are interchangeable. It is an angle. Some unknown angle. So now we've got it down to one fraction. But we can clean it up further. We have to recognize it though. And this is where our lack of history with this could be a problem. The numerator, 1 minus cosine squared, that again comes back to our original identity that says sine squared plus cosine squared equals 1. If I subtract cosine squared from each side of this equation, which I'm allowed to do with algebra, yes, this is the exact same equation. It's the exact same thing, yes? All I did was move the cosine squared to the other side of the equation. Perfectly legal in algebra. That is exactly what that means. What I've got right here is my numerator, right there, which means I'm going to take this and I'm going to plug it in for the numerator. Because then your numerator, instead of being two terms, is only one term, which is simpler. And then it's going to get even better, because once we do that, then what can happen? The sign on top and the sign on the bottom can be reduced. So we can cancel sign from the denominator with one of the two signs in the numerator, which eliminates the squared, and turns this expression into sine, shouldn't put equals, there's no equal sign, sine over cosine, which if they had told us to only use sine and cosine, this would be where we would stop. But they didn't. They said simplify. Is sine over cosine something we should recognize? That's what? That is tangent. Sine over cosine is tangent. So our simplified answer would be that cosecant secant minus cotangent is equivalent to tangent. That is fully simplified. Okay? That's how this works, guys. All right, let's do one more example and then we'll end today. Let's do example 4. Okay, and I do worry a little bit that he's going to crowd us on space here, but we'll make this work. Matter of fact, I'm going to make it work real well, real fast for us here by doing this. Now I have a lot more space. Okay, true, you don't, but I do. So, okay, again, we start off, we write everything in the entire expression in terms of sine and cosine. So we just start with cosecant is 1 over sine. So we go, okay, that's 1 over sine x times cosine x, which we don't need to change because it's already in terms of sine and cosine, plus cotangent, which is cosine over sine. We use our reciprocal identity to write cosangent in terms of cosine over sine. That's the numerator. Then in the denominator, secant is 1 over cosine, and cotangent is cosine over sine. So we rewrite everything in terms of sine and cosine. Now, from there, we look, does anything cancel? What? On the denominator, cosine x would cancel, but that's it. Nothing else cancels. Okay? We can't cancel bottom to top yet because there's a plus sign on top, which means we have invisible parentheses protecting the numerator from any canceling. Okay? We can't cancel until the numerator is one term and the denominator is one term. Then maybe we can cancel. Okay? So we multiply out what's there. So on top, the first term here, 1 over sine times cosine, is cosine over sine. Second term can't be simplified. It stays cosine over sine. And in the denominator, we have 1 over sine. Now the numerator of that expression is still 2 terms. Do we need to do anything to get a common denominator? Don't they already have a common denominator? They're both already over sine x, yes? So I'm just going to add those together. I'm going to add cosine over sine plus cosine over sine. Those are the same thing, right? So when I add an expression like, say, z plus z, what do I get? 2z, right? So when I add those two fractions together, I get 2 cosine x over sine x, and that's still over 1 over sine. Oh no, we have a fraction within a fraction. So, how do we deal with that? Okay, good. We multiply the numerator and denominator by the reciprocal of the denominator. We flip the bottom and multiply. The whole point being that all of this cancels. The entire point of doing that is to cancel the entire denominator. Now in the numerator, what happens with the signs? These cancel as well. And we are left with 2 cosine x, which is as simple as this could possibly get.